Hi guys. Today I'm going to teach you how to do an AP Physics problem because I need the extra credit. And my teacher, well, let's just say he's a little bit out there. Alright, so the problem is going to be from 1991 and it's the first Mechanics 1 problem. I'll read you the problem and then I'll show you the diagram they have. A small block of mass 2m initially rests on a track at the bottom of the circular, vertical loop-the-loop shown above, which has a radius r. The surface contact between the block and the loop is frictionless. A bullet of mass m strikes the block horizontally with initial speed v and remains embedded in the block as the block and the bullet encircle the loop. Determine each of the following in terms of m, v, r, and g. Okay, so there's the diagram. I don't know if you can see it well, but I drew my own because I feel like it's better. Well, you guys can see it better at least. Okay, so here's a loop-de-loop. You see the bullet over here. The block is there. Here's the loop-de-loop with the radius r. Here's the point P that they'll be asking us for later. And for future reference, let's say that we're going to zero out the potential energy at the ground. Okay, so the first thing that they're looking for is the speed of the block and the bullet immediately after impact. Alright, so does anyone know what we're supposed to do here? Alright, well, you're not going to give me a response, so I guess I'll tell you anyway. We're supposed to go to the law of conservation of momentum. See? Here. Momentum initial is going to be equal to the momentum final. There you go. See? Alright, so basically this means that the mass of the bullet times the velocity of the bullet plus the mass of the block times the initial velocity of the block is going to be equal to the sum of the masses times the final velocity after impact. So the equation should look like that. But since we know that the block starts off at rest, we can cancel that out, and so that goes to 0. And so what we're going to have is the initial mass and velocity of the block multiplied together is going to give us the total mass times the final velocity. See? Alright, so basically all we do then is solve for the final velocity. Okay, so we have the mass of the bullet times the velocity of the bullet over the total mass is going to be equal to the final. See? Alright, and the m's cancel because they're the same. And so all we're left with is the initial velocity of the bullet over 3 is going to be the velocity immediately after impact. Yay! We got part A done. Alright, now for part B. For part B, they're asking the kinetic energy of the block and the bullet when they reach point P on the loop. Alright, well, point P is right here. Okay, so what we're going to go to here is the law of conservation of energy. So the energy at the bottom of the loop-to-loop is going to be equal to the energy at the top. See? There we go. Alright. At the bottom, since we zeroed out the potential energy, we're only going to have kinetic energy. But once we reach point P, we're going to have both kinetic energy and potential energy. So we write KE at the bottom is going to be equal to the potential kinetic energy at P plus the potential energy at P. Got it? Alright. And what we'd be solving for is the kinetic energy at P. Sorry. So the kinetic energy at P is going to be equal to the kinetic energy at the bottom minus the potential energy at P. Can you see? Alright, new page. Okay. Since we know that the kinetic energy is going to be equal to 1/2 mv squared. We substitute in at the bottom the total mass for the mass, and V, what we found is V final in relation to V initial. So it's going to be 1/2 times 3m, which is the total mass, times V initial over 3 squared. Because that's the... Matt, can you see? Alright, no, I don't think you can. Yeah, you can. Alright, so that's the velocity right after the bullet hits the block. And that's the velocity that we're using because it's at the bottom and that's what we need. And we're going to set that equal, well, no, that minus the mass, again, which is 3m, times gravity, times the height, is going to be, hold on one second. Alright, so we're going to have minus 3 mgr is going to be equal to the Ke at P. So that's our equation. Basically what we're doing now is we're going to, we're going to solve that out, I believe. Yep. Alright. So, sorry, I'm a little bit lost right now. Just kidding, I got it. Alright, so when we solve that out and we simplify it in best terms, well, in the simplest terms, we get the kinetic energy at P is going to be equal to the mass times the initial velocity squared over 6 minus 3 mgr. That's just combining these two as best as possible. Alright, part B, success. Alright, one more part left and we're done. So part C is asking for the minimum initial speed, V minimum, of the bullet if the block and the bullet are to successfully execute a complete circuit of the loop. Okay, well, in order for this to work, we're trying to find the Vmin so that the block and the bullet can go up and all the way down. So we start at the very top. At the very top, the centripetal force is just the weight. So we just write that. Fc is equal to weight. See? Alright, but the centripetal force is going to be equal to mv squared over r. That's just a formula that we know. And the weight is going to be equal to the mass times the gravity. So that's what we have. And as you can see, the m's cancel. The m's cancel, and then we want to solve for v, because we want to find the minimum velocity. So v is going to be equal to the square root of gr. See? Hooray! Alright, but we're not done yet. Because we want to find the velocity that we need to start to get all the way up here, we have to use the law of conservation of energy again. So the kinetic energy of both the bullet and the block at the bottom is going to be equal to the kinetic energy of the bullet and the block at the top plus the potential energy of the bullet and the block at the top. So let's write that out. Kinetic energy at the bottom is going to be equal to the kinetic energy at the top plus the potential energy at the top. Gotcha. Alright. So we know that the kinetic energy at the bottom is going to be equal to 1/2 times the total mass times the velocity that we found. Basically, we're using what we used up here and bringing it down here because it's the same thing. This is equal to the kinetic energy at the bottom, and this is equal to the kinetic energy at the bottom. So that's what we're using. So the initial velocity over 3 squared is going to be equal to the kinetic energy at the top of the loop-to-loop. So we have 1/2, again, times the total mass. But this time, we use this v that we just found, because that's the v at the top. So radical gr squared plus 2r, because that's the height, times the total m, so 3m times g. So you get 6 mgr. Sorry, I had to squeeze that in. I didn't realize how big I was writing. There we go. Okay. So we can basically divide each side by the half, so the halves cancel, and the m's also cancel. So we are left with 3 times the velocity initial, 3 squared. It's going to be equal to 3 times the square root of gr plus 12 times gr. But we can also factor out the 3 again. So we're going to get VO squared over 9 is equal to radical GR plus 4GR. Oh, not the radical, because we squared that already. So we have V initial squared over 9 is equal to 5GR. Equal to 5GR. So we multiply the side by 9, and we get VO squared is equal to 45GR. And we want to find the velocity, so we take the square root and get 45GR. Now, technically that is the answer, but we can simplify the radical, because 45 is 9 times 5, and 9 is a perfect square. So we can take out, hold on one second please. Okay, so we can take out the 9 as a 3, and we have 3 radical 5 times GR. See, that is our answer. And I believe we're done. Okay, so let's run through this really quickly again. To find the speed after impact, we're going to use the conservation of momentum, and that's just the mass times the initial velocity. The sum of the masses times the velocity initials is going to be set equal to the sum of the masses times the final velocity. Then for B, we're just going to use energy conservation, and as long as we remember to zero out potential energy at the bottom, it makes life a lot more easier for us. See? And then the same thing is done for C, as long as we remember that the centripetal force at the top is going to be equal to just the weight. Okay, I hope I've been somewhat of a help. If not, feel free to contact me and I'll try to clear this up a little bit more. I think that's it. Thank you for your time and patience. Bye!